Greetings. So welcome to today's session. So if you recall where we stopped in the previous session, we were looking at the PID controller, and we looked at the characteristics of each component of the proportional, integral, and derivative controller. We also looked at how the control design problem essentially boils down to selecting the controller parameter, or what we call as controller gain, right? So that's where we stop, and ultimately we need to ensure that the closed loop system is stable and meets some expected performance requirements, right? So that we achieve the desired response, from the closed loop system. So that's where we stop. So today's class, I'm going to start with the answer to your question which I posed to you, right? So that is, how do we convert, a performance regions of closed loop, right? So consider let's say that someone gives us the specification, the settling time should be less than 4 seconds, and peak overshoot should be less than or equal to 10%. Okay? So the task for us is to obtain the corresponding region of closed loop. That is, how do we convert these performance requirements into corresponding regions or closed loop? That is an important step, right? Isn't it? If we want to essentially apply the analysis that we have been learning, we should be in a position to design the closed loop system for stability, which will require that all closed loop poles lie in the left of complex, right? Then require the closed loop system to satisfy some performance requirements. So the question, in another sense, can be viewed as one wherein we want to ask ourselves the point that okay, for closed loop stability, we require all poles to be in the left of complex, right? So to ensure closed loop performance, can we say that we require our closed loop poles in a sub-region in the left of complex to meet these given specifications, right? So that's what we want to ask ourselves. So let's see how we do this. So if you recall, and as I mentioned, typically the performance specifications are given by looking at the step response of the first order system or under than second order systems. So that's the convention. So recall that, the settling time expression, right? So was 4 by zeta omega n, right? So as I mentioned, by default we will use the 2%, and that should be less than or equal to 4 seconds. So this will imply that zeta omega n should be equal to greater than or equal to 1, right? So this implies that minus zeta omega n should be less than or equal to minus 1. Okay, why am I writing like this? Please note that the inequality will be flipped when I multiply the inequality by minus 1 on both sides. So the reason is that, please recall that the poles of the underdamped second order system are minus zeta omega n plus or minus j times omega d, where omega d is nothing but omega n times the square root of 1 minus zeta square, right? These are the two poles of the underdamped system. Now, why do we write like this? Suppose if we look at the S-plane, okay? We look at the we plot the S-plane, and we essentially look at the real axis and the imaginary axis. So let us say we draw a line, see, please note that minus zeta omega n is the real part of the pole, right? So suppose if I, suppose if I draw, a vertical line, like at -1, which is what we have calculated. So let's say this is -1, and I draw a vertical line passing through -1. We can immediately observe that all poles or all values of S to the left of this vertical line will have a real part less than -1, right? I am sure all of us are in agreement with that. So consequently, the equivalent way to look at it is that, like, if we have all the closed loop poles to the left of this vertical line at -1, the corresponding settling time will be less than or equal to 4 seconds, right? Because how did we get this minus zeta omega less than or equal to -1? Because we looked at, we wanted settling time to be less than or equal to 4 seconds, right? So that's how we got this constraint, right? Isn't it? So the physical meaning of this vertical line is that, like, if we have all the all the poles to the left of this vertical line at -1, we'll have the settling time to be less than or equal to 4 seconds. Okay, so that is the physical implication. I hope it is clear how we converted the settling time specification into a sub-region of the left-of complex. Please note that we wanted all the closed loop poles to be, first of all, in the left-of complex plane for closed loop stability. Now we are looking at performance specifications, right? So once again, the overall objective of this exercise is to identify a sub-region in the left-of complex plane where we can place the closed loop poles and the closed loop system will satisfy performance requirements, right? So that is the idea. All right. So now, going ahead, we wanted the maximum peak overshoot to be less than or equal to 10%, right? So please remember what was maximum peak overshoot. It was exponential of minus zeta pi divided by square root of 1 minus zeta square times 100%, and that should be less than or equal to 10%, right? So this implies that e power minus zeta pi divided by 1 minus zeta square should be less than or equal to 0.1. Okay, so how do we solve for this inequality? Okay, first I leave this to you as an exercise. First, solve the equality. Okay, so solve the equality e power minus zeta pi times square root of, divided by square root of 1 minus zeta square is equal to 0.1. If you do this, I leave it to you as an exercise. You will see that you will get zeta to be 0.591. All right, and for this satisfying this inequality, you can immediately find out that zeta should be greater than or equal to 0.5. Okay, so that's what you will get as this. Okay, so to essentially ensure that you have this constraint being satisfied. Okay, so please note that this is with a negative exponent, right? So obviously, that's why we get a lower bound of zeta, right? For all zeta greater than or equal to 0.591, this exponential term, right? E power minus zeta pi divided by square root of 1 minus zeta square will be less than or equal to 0.1. Okay, so I leave this here as an exercise. Please let me know. Please do it. If you have any questions or concerns, please feel free to ask in the next session. Okay, regarding this point. And recall that cos beta is equal to zeta. Do you remember what was this beta? Do you remember what this angle beta is?
Angle from origin to the point in the S-plane.
To the very good, to the complex conjugate pole, right, for the second order system, right? Isn't it correct? Yeah. Yes. So if I can go there, so you can see this beta being marked here, right? So you draw a line from the origin to the complex conjugate pole, right? So whatever is the angle which is made by that line is what is beta, Correct? Yeah. Now, if zeta has to be greater than 0.591, we will get beta to be less than or equal to cos inverse of 0.591. Cos inverse of 0.591 is 53.77 degrees. Okay, how did we get 53.77? It is cos inverse of 0.591. Okay, so please note that cosine of theta decreases with increase in theta, right? So we want the cos beta to be greater than 0.591. Consequently, beta should be less than or equal to 53.77. Okay, so that is what we need to essentially look at. I hope it is clear, right? So what it is, right? All right. So with this, we can immediately see that we have essentially reduce this problem, of having the peak overshoot to be less than 10% to an equivalent region in the S-plane where I draw, two lines that make an angle of 53.77. Okay, so this angle is 53.77 degrees, and all poles, okay, which lie within this region will satisfy the constraint of the peak overshoot to be less than 10%. I hope my point is clear, right? So, all right. So essentially, what we have done is that, like, we have converted the requirement on the peak overshoot into a sort of like a conical region, right, in the left of complex plane. So you slowly get the idea, right? Each performance specification, we are essentially deriving an equivalent subregion in the left of complex plane. Now we want to satisfy both the conditions, right? That is settling time less than 10% and less than or equal to 10%, and peak overshoot less than or equal to, settling time less than or equal to 4 seconds and peak overshoot less than or equal to 10%. That's going to be the intersection of these two areas, right? So we are the intersection of these two regions is going to be this. So the region which I'm shading in red color, okay, will be the resultant desired location of closed loop. Okay, so you can see that it's in the form of an open trapezoid, right? So that is going to be the region which will satisfy, okay, both settling time less than or equal to 4 seconds and peak overshoot less than or equal to 10%. Okay, I hope this is clear, right? So any questions on this? Okay. So you can immediately see that we have got a sub-region, okay, in the left of complex plane, wherein, like we can observe that, like we will be able to satisfy both the performance specifications. Now, if we are able to place our closed loop poles in this region, we are assured of this performance, right? So we can immediately see that if all our closed loop poles are in this sub-open trapezoid, then we are done, right? So we ensure both closed loop stability and closed loop performance. Okay, so that is a big advantage for us. I hope the argument is clear. All right. Okay. So any questions on this before we proceed to a few examples? All right. Okay. So so let us do a few examples. Okay. One, in fact, application, like of closed loop control is to essentially stabilize a previously unstable system or plant. Okay, so let's recap what we constructed. Please remember that the plant transfer function, we could write it as P of S. The input signal is U of S, the output is Y of S. We have a reference input R of S. And then what we do is that we compare, and we take feedback, and we essentially have this feedback path transfer function and P of S. Okay, this is what we have, right? So this is our standard closed loop feedback system which we consider, right? So please recall that the closed loop transfer function was G of S divided by 1 plus G of S H of. Okay, let us say, okay, of course, where the function G of S is going to be the product of C of S and P of S. Okay, so this is something which we already are aware of, and G of S H of S is what is called as the open loop transfer function. Okay, so please recall all these definitions and terminology, right? Okay, so now let us do one example. Okay, let's start with the first example, right? So let us say we have a plant whose transfer function is 1 by S minus 1. Okay, so is this system stable or unstable?
Unstable.
Why? No, sorry.
Pole is on the right side of the RS S-plane.
Very good. So we can see that pole is at +1, okay, which means that to begin with, the system is unstable. All right, very good. Okay, so now the question is, or the task or the exercise we will do is that let us attempt to stabilize the system, this plant, using a unity negative feedback to begin with. So what is the implication of feedback being unity feedback? It will imply that H of S is 1, right? So that's something which we, okay, so we will have our feedback path transfer function H of S to be unity. All right. Okay. So let's first attempt proportional control. Okay. So we'll start with the simplest control. Okay. So proportional control is the simplest one. So what happens is that, like, if you have proportional controller, the controller transfer function C of S becomes equal to Kp. Okay. So if it is Kp, what happens is that, like, G of S, which is going to be equal to C of S multiplied by P of S, is going to be equal to Kp divided by S minus 1. Right? H of S is 1. So the closed loop transfer function is going to be equal to G of S divided by 1 plus G of S H of S. So that's going to be Kp divided by S minus 1. That's G of S divided by 1 plus Kp divided by S minus 1. Why? Because H of S is 1, right? So we have Kp by S minus 1 divided by S plus Kp minus 1 divided by S minus 1, right? Isn't it? So I'm just taking LCM in the denominator, right? So this S minus 1 will get now cancelled. So as a result, the closed loop transfer function, which is nothing but Y of S by R of S, okay, is going to be equal to Kp divided by S plus Kp minus 1. Right? So I hope everyone is clear, right, about this. So now, what is the closed loop characteristic equation?
S plus Kp minus 1.
S plus Kp minus 1 is the closed loop characteristic polynomial. So consequently, the closed loop characteristic equation is going to be S plus Kp minus 1 is equal to 0. Right? That's what we have. So consequently, S will be equal to 1 minus Kp. Right? So this is the closed loop pole. Right? Because we know that the solution of the closed loop characteristic equation is a closed loop pole, right? Is it not? Correct? Yeah. So we have 1 minus Kp as a closed loop pole. Now, when will this closed loop pole lie in the left of complex plane? For what values of Kp?
Kp less than 1.
Very good. Why? Because the closed loop pole should be in the left of complex plane, right? So this is only there is only one pole. So obviously that pole should be on the negative real axis, right? So the question is, when will 1 minus Kp be negative, right? 1 minus Kp will be negative only when Kp is less than,
1.
sorry, only when Kp is greater than 1, right? Sorry. Yeah.
Yes, Kp
See,
greater than 4.
so 1 minus Kp should be less than 0, right, for stability. So this will imply that Kp should be greater than 1, right? So that is the criteria. So consequently, the closed loop system would be Bibo stable. Some people will call it as asymptotically stable. We'll see why later on. Okay. So Bibo asymptotically stable. Okay. For all Kp greater than 1, right? So we have essentially figured out that if we have a single parameter, this is the controller parameter space, right? In this case, so this is our origin, and let's say this is 1, right? For all values of Kp greater than 1, which is this side, okay? So this is Kp greater than 1, okay? So the closed loop system is asymptotically stable, okay, or Bibo stable. All right. So I hope this is clear. So what we have done is that, like, we have taken a very simple example, and in this case, we have observed that using proportional controller, we have been able, to stabilize the closed loop system. All right. So, and we have been able to find a range of Kp, that will stabilize the closed loop system. So immediately, we get a feel of where the analysis is going, right? Isn't it? Because we can immediately observe that we want to essentially get subregions of the controller parameter space that will achieve closed loop stability. See, initially, we had Kp to be a real parameter, right? So we can choose a value of Kp between minus infinity to plus infinity. Now, through this analysis, what we have done is that, like, we have essentially narrowed down this region to Kp greater than 1. So which by itself is a big what to say task, right? So that's what we have been able to achieve. All right. Okay. Fine. Okay. Any questions? So now let's consider another example, okay, wherein we consider the Planck transfer function to be 1 by s squared minus 1. Here, what are the poles of the system?
minus 1 plus 1.
Minus 1 and plus 1. Okay, very good. So is the system unstable or stable?
Unstable.
Unstable, right? Because one pole is in the left of complex line. So this is once again unstable, right? So let us once again try to see whether we can stabilize this unstable system using, to begin with, the proportional control. So let's say we take C of S to be equal to Kb. Okay, once again unity feedback, right? So what is it? Stabilize using unity negative feedback. Okay, so that's what we are trying to do, right? Once again. Okay, So if C of S is Kp, we follow the same process. G of S is going to be equal to C of S times P of S, which is going to be equal to Kp by S squared minus 1. H of S is anyway unity, right? We are given that H of S is 1 because we are having unity negative feedback. So we follow the same process. Once you do a few examples, you will get a hang of this, right? So the closed loop transfer function is going to be G of S divided by 1 plus G of S times H of S. So what we will have is the following. We will have Kp divided by S squared minus 1 divided by 1 plus Kp divided by S squared minus 1. If you take the LCM, the denominator, we will have Kp by S squared minus 1. And then like S squared plus Kp minus 1 divided by S squared minus 1, right? So the S squared minus 1 will cancel off. So what are we left with? We will be left with Kp divided by S squared plus Kp minus 1. Alright, so that's what we'll have. So consequently, the closed loop characteristic equation is going to be equal to S squared plus Kp minus 1 equal to 0. So what would we have for the closed loop poles? We'll have closed loop poles as plus or minus square root of 1 minus Kp. Alright? Okay. So now looking at this, we can have three cases, three scenarios, right? Kp greater than 1, Kp equal to 1, and Kp less than 1, right? We can split it into three cases. What do you think will happen when Kp is greater than 1?
Poles on the imaginary axis itself.
So we are going to have closed loop poles on the j omega axis, right? Is that something which is desirable? No, right? As we discussed, so it depends on our perspective, right? So we can call it marginally stable or critically stable and so on. But certainly we don't want closed loop poles to lie on the imaginary axis. Absolutely not. Okay, so that's something which is not desirable. Okay, so that is point number 1. Now, what happens when Kp is equal to 1?
Poles on the origin.
So we have two repeating poles on the origin, right? So we are going to have a closed loop pole repeating at 0, right? Repeating at the origin, right? So once again, is that something which we desire?
No.
Certainly not, right? So we don't want closed loop poles to repeat at the origin. Absolutely not. Okay. Now what will happen if Kp is less than 1?
Poles on both on the left side and right side.
So one pole on positive real axis, right? I should say one closed loop pole, okay, to be very precise, okay, and one closed loop pole on negative real axis, right? So is this something which is desirable? Once again, no, right? Because you see, this will make the closed loop system unstable, right? So what does this imply? This entire exercise, this implies that this system, this plant, which we are given, whose transfer function is 1 by S squared minus 1, this plant or system cannot be stabilized. Okay, using a proportional controller. Okay, so that is the bottom line. See, it is not necessary that every system or every controller works with every system. Okay, so I hope the crux of this exercise is clear, right? So we tried out proportional control because it is a very straightforward and simple controller to start with. We saw that although it worked in the first example, the second example, it doesn't work. Okay, so then we move on, right? So just because the proportional controller doesn't work, like we should not stop, right? So we just move on. Okay, so now we go to the next control. Okay, so let us try proportional integral control. So let us try PI control. So what do we have for PI control? Our C of S becomes Kp plus Ki by S. This I can read it as Kps plus Ki, the whole divided by S, right? Is it not? That's what we have. So then what we will have is that the transfer function G of S to be equal to C of S times P of S. That's going to be equal to Kps plus Ki divided by S, and the plant transfer function is 1 by S squared. Okay, so this is what we'll have. All right. So this we can simplify it as Kps plus Ki divided by S cube minus. Correct. Okay. So now the closed loop transfer function is the following. So it will be G of S divided by 1 plus G of S S of S. This can be written as Kps plus Ki divided by this cube minus S, the whole thing divided by 1 plus Kps plus Ki divided by S cube minus. Okay, so if I take the LCM once again, I will have Kps Ki divided by S cube minus S. Okay, then I will have S cube minus S plus Kps plus Ki divided by S cube minus S. So we cancel off S cube minus S. So what are we left with? We are left with Kps plus Ki divided by S cube plus Kp minus 1S plus Ki. All right. So now we can see that the problem is becoming more and more complicated, right? So now the closed loop characteristic equation is going to be S cube plus Kp minus 1S plus Ki equal to 0. So we can see that this is a third order equation, right? So the closed loop characteristic polynomial is of order 3, and the closed loop characteristic equation is a third order polynomial equation, right? So that's something which we can readily observe. Now, what do we do? That's the question we need to ask ourselves, right? So see, we have come that far. Now we need to figure out, like what can we do in this case, right? In the previous case, at least we had a quadratic equation. We could solve for the roots, and then we could argue, and it was only one parameter. What to say? Then we could essentially figure out whether there existed a KP, like which will ensure that both the roots lay on the left of complex plane. But now we have two parameters, right? So now the challenges are, right? It's a third order equation, right? Third order polynomial equation, and the characteristic polynomial is a third order polynomial, right? And then there are two parameters, Kp and Ki, right? So the problem has become a little bit complex, right? That is, like, how can I find Kp and Ki, which will stabilize this closed loop system, right? So how can we do this? Can you think of some method?
If you make the polynomial as a Hurwitz polynomial, then all the poles will be on the left side only, right, sir?
I'm sorry, what is it?
If the coefficients are positive, if we say kp minus 1 is positive and k is positive, then the polynomial is a Hurwitz polynomial whose roots are only on the left hand side of the plane. Then the system is stable. Then the system will be stable. Is it correct?
Okay, that's a good start. But however, it is not sufficient that all coefficients be positive. Okay, so we will shortly see in the next class. What is the equivalent condition, right? So it essentially means that if you are given an nth order polynomial, right, and you want all the n roots to be in the left of complex plane for the polynomial to be Hurwitz, right? So then how do we find that, right? So that is exactly the general question we are asking. Okay, in this specific case, we are asking, hey, how can I find Kp and Ki to, if at all they exist, such that the three roots of this equation lie in the left of complex plane, right? In general, we can ask ourselves this question. Okay, so if you pose the general problem, okay, consider an nth order polynomial. So consider an nth order polynomial. Let's call the nth order polynomial as some ds, which is a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 all the way till an minus 1 s plus an. Okay, all right. So now the question becomes, how can one determine the distribution of roots of this polynomial? Without calculating them. See, if you want to solve for roots, once again, particularly when you have these unknown parameters, it's going to become very, very difficult, right? On the other hand, we just only want conditions on the coefficients, right? Yeah, such that the polynomial is Hurwitz, the closed loop characteristic polynomial is Hurwitz, right? So this is the main question, right? So we consider an nth order polynomial in general. We want to find out, under what conditions on the coefficients, can we have all the n roots in the left of complex plane? Okay. The more generic question is to figure out how do we find the distribution of roots of this nth order polynomial, right? Without calculating. That's important, right? Because if we are able to come up with such a method, then what will happen is that we will be able to tell, hey, look, these are the conditions on the controller parameters such that the polynomial will become Hurwitz, right? So that's something which you and I can readily suggest or tell. Okay, so that is the idea here, right? Behind having a generic method from which we could analyze, what will be the distribution of roots of an nth order polynomial, and the connection to our analysis is that we will be able to get the regions of the controller parameters of the controller gains that will ensure that the closed loop system is stable, okay, if at all it is possible. Okay, so I hope the link is clear. All right, yeah. Okay, so any questions on this? Okay, so what we will do is that we will continue from this point in the next class. Okay, we will find the answer to this general question, and then we will see how we could essentially apply this concept to our problem of control design and determining the appropriate range of controller parameters for ensuring closed loop stability. Okay, so that's something we will continue in the next class. All right.
Professor, one doubt, Professor.
Yeah, please go ahead.
Last class we discussed, no, sir. What if if the system is non-causal? What if the numerator roots are greater than denominator? You told that we can discuss in the next class. You will inform in the next class.
So yeah, could you think about it? No.
I thought about this, but I'm not getting any clue over here, sir.
All right. Okay. So maybe what you can do is that, like, you can just think through till the next class. Okay. Then we will come back to that. Okay. Please remind me in the next class. Okay. So that you get some more time. All right.
Okay, Professor.
All right. So, yeah. Okay. Any other questions? Okay. So if not, we will continue in the next class. Okay. Thank you.